Well, hello everyone. We're gonna jump right into our first OChem chapter, and this is going to be laying a very important foundation. First of all, what is even organic chemistry? Why are we studying it? As well as building, as I said, a foundation for a lot of important concepts that are going to be underlying for um, the remainder of this semester and even going into the next semester as well. So we're going to jump right into it. Again, you should be following along on your own notes. Whatever I write down, you should write down, and we'll just kind of go through all this together. So um, this first page is kind of sort of a joke, but sort of kind of serious. But this is the kind of world that us organic chemists live in. This is our periodic table, and it looks kind of silly, but really emphasizes what we are studying when it comes to organic chemistry. Um, OChem is sort of known as the chemistry of life. But it's even more than that because it can apply to non-living objects. But basically, anything that has carbon in it is going to be something that falls under the organic chemistry realm. The reason why it's called the chemistry of life is because any living system is going to have carbon in it. You and I are full of carbon atoms. It's the most prevalent atom in your body next to oxygen. Now, if you think of that, like most of our body is water, that's where all the oxygen is coming from. But after that, the next most prevalent element is carbon. And so you can find it in every single aspect of that. But not only that, if you just take the human system, for example, everything that happens in your body is dictated by organic chemistry. It's organic chemistry reactions that keep your system alive. It's organic chemistry that causes all of the chemical reactions that go on within your body, from the process of respiration and what your body does with oxygen to the process of digestion, to even organic chemistry governs the firing of your synapses in your brain, and all of those things. The physical uh, movements, how your muscles work, that is all governed by organic chemistry reactions. Um, Now, what makes carbon such an amazing um, atom? Carbon mostly forms covalent bonds, and that's what we tend to study in OChem. In general chemistry, you looked a lot at molecules that were dealing with ionic, and did a little bit of covalent bonding, but mostly in organic chemistry, we're going to be looking at covalent bonds. And carbon's kind of in that sweet spot. It forms usually four covalent bonds. And we'll see a couple exceptions to that periodically. Um, but more importantly, it has a great mix, now that's the technical term, but a great mix of reactivity as well as stability. So it's reactive enough to form new substances, which is important. I mean, it's key for keeping you alive. But it's also stable enough so that it just doesn't react with anything and everything, and then your body just kind of falls apart. So it's got that kind of sweet spot of it's very reactive. It can form bonds. It can accept electrons. It can donate electrons in various types of reactions. And when it has reacted, it will form stable compounds. So there's that kind of nice mix of reactivity and stability. Just to kind of, highlight some specific compounds that we call organic in your human system: DNA, things like proteins, enzymes. These are all compounds that have carbon as their main atom within their molecular structure. And so we'll just kind of jump right in. Now, before we go into anything specific, there are a lot of important things I'd like you to review. I'm going to assume you're masters at these already because you passed general chemistry. But these are things I'm going to assume that you know, and I'm not going to cover specifically or review specifically in class. So kind of take a look at this list. I might highlight a few of these and kind of show you some important trends, but I'm going to assume that you know these terms and are masters at all of these things. So organic chemistry is kind of founded on the structural theory of matter, which it basically says that substances are defined by a specific arrangement of atoms. And here's what I kind of mean by this. I want to draw the structure of two compounds that have the exact same molecular formula. So they have the same number and the same kinds of atoms, but here's a very important thing. Their properties are drastically different. This compound on the left has a boiling point of negative 23 degrees Celsius. That means it's a gas at room temperature. And this one over here, with the same formula, has a boiling point of about 78 degrees Celsius. So same formula, but because the atoms are arranged differently, they have different properties. They're different compounds entirely, even though they have the same molecular formula. And this kind of leads us to our first, we're going to talk about many different types of isomers throughout OCHEM. But our first important type of isomer that we're going to look at are known as constitutional isomers. These are compounds that have the same molecular formula, but different connectivity. Now, I'm going to dive deeper into constitutional isomers in a little bit, but I'm going to take a little bit of a rabbit trail and focus on something that you learned in general chemistry, but it's going to be important for OCHEM. And then we're going to take it a step further with drawing structures in organic chemistry. So I'm just going to kind of do some examples of drawing Lewis structures, and then as I said, we'll take it a little bit of a step further. So when you draw a Lewis structure, and all the ones that we're going to be drawing pertain to organic molecules. Um, First thing you always do is count the valence electrons for all the atoms. Now, valence electrons, those are the ones in the outermost shell. You can look at a periodic table, remember your periodic trends, and you probably just want to start committing things to memory for organic molecules. Like, for example, carbon always has 4 valence electrons. Just memorize that. Um, Hydrogen, remember this from general chemistry, always has 1 valence electron. And then there's 2 of them here for hydrogen. And then all the halogens always have 7 valence electrons. And we got 2 of those there. So if we add all of that up, let's see, that's 4, 6, and 10 plus 14, that's 24 valence electrons. So our compound should have 24 in there. Let me see, did I do that right? 14, 15, 16? No, sorry, 20. I'm sorry, 20 electrons. Now, when it comes to drawing organic structures, you want to put atoms other than hydrogen or oxygen, and I'm going to add halogens to this. You use X as a generic halogen. Those are going to be the ones in the middle. Sometimes you might have oxygen in the middle, but commonly you'll put it on the outside. So in a compound like this, I'm going to put carbon in the middle, and I'm going to put my hydrogens on the outside as well as halogens. And the reason I'm always going to put carbon in the middle is because it's the one that's going to form 4 covalent bonds around it. And I'll start by putting carbon with its 4 valence electrons, hydrogen, each with their 1, and bromine, each of them have 7. And then I'm just going to start pairing electrons up. So I'm going to make a bond here, a bond here, a bond here, and a bond here. Again, the reason we do this is so that all the atoms fulfill the octet rule. Or hydrogen, hydrogen's happy with two. We don't ever usually, yeah, we don't ever show hydrogen with more than two around it. And rather than, have all these dots and X's everywhere, we just simply use lines or dashes to show bonding electrons. And then we do our dots for non-bonding electrons. As we get more and more deeper into OCHEM, I'm not always going to show every single lone pair. Usually I'll show the ones that are important if they're involved in reactions or things like that. But, in the beginning, I'd like you to draw out all of your lone pairs. All right, so let's do some more examples here. So again, now here we have, carbon, hydrogen, and nitrogen. If I just start adding up all my valence electrons, that comes out to 14. Nitrogen has 5. That's just something to memorize. And I'm going to start by putting carbon as a central atom. Nitrogen will be out here. And then I'm just going to start putting hydrogens around. Now, over time, I'm not going to, I have five hydrogens here. I'm going to show you something really wrong. I'm not going to put all 5 around this carbon. Okay, why is that? Well, I know that carbon can only form 4 bonds to it at most, or 4 single bonds, I should say. And so by putting 5 hydrogens around that carbon and, not leaving any for nitrogen, it's going to it's going to violate the octet rule left and right. So I'm going to put a couple of hydrogens around the nitrogen. Now I'll give carbon its 4 valence electrons, each hydrogen 1, and then I'm going to give nitrogen 5 valence electrons. And now I'm just going to start pairing them all up. So I can make a pair here, 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 and here. And then I'll pair these up around the nitrogen. And so that Lewis structure will look like this. And nitrogen's got its lone pair on it. And if we kind of take a step back and see everything should still obey the octet rule when it comes to carbon and nitrogen. All the hydrogens are happy with 2. I don't go over that 8 number, that the value of 8. And so that's the Lewis structure for that compound. Now in this one, here we have 18 valence electrons. And this one kind of gives you a little bit of a hint that you should be using multiple bonds. And here's kind of a way, or you'll kind of demonstrate a little bit about how we know that we should be doing this inherently. And I'm going to put carbons in the middle and oxygens around here. Now, what do I do with these hydrogens? Well, I can start putting them, let's just start putting them around this carbon here. And I got 1 left, so let's maybe put it on this carbon. And let's see if we can come up with a structure, a Lewis structure that still fulfills the octet rule for all of these atoms. So I'm going to give carbons, each of them 4. Each hydrogen's going to get 1. And this oxygen is going to get 6. Now I'm going to start pairing everything up. So here, 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 and here. If I just do a quick counting, I can see that carbon's going to be happy. It's got 8 around it. With this one here, I'll pair these up. And if I stop there, both the carbon and the oxygen are not happy. They don't have a full octet. So how do I fix this? Well, I'm going to share another pair of electrons. So those 2 atoms, the carbon and the oxygen, are going to be sharing two lone pairs, or not two lone pairs, but two pairs of electrons now. And so what does that Lewis structure look like? Well, if I share four electrons between an atom, that's going to form a double bond. And oxygen has two lone pairs. Now, to kind of wrap up this lecture, oh, actually, sorry, I have one more example to do. Sorry about that. This kind of emphasizes another type of notation that we'll see a lot in chemistry. So we have these, what we call condensed formulas. These kind of tell you a lot more than a molecular formula because they kind of imply what the connectivity of the atoms should be. Not a lot of, I don't want to say guessing, but you don't have to try to visualize what atoms are attached to which atoms. And so it's very important to be able to read how to read a condensed formula. And so when it comes to hydrogens, the hydrogens are usually attached to the atom that precedes it. So I'm going to show something where those three hydrogens are on that carbon. Now this oxygen here is going to be attached to both this carbon and this carbon. And then these three hydrogens are going to be attached to that carbon. So when I'm going to draw the Lewis structure for this, I'm going to have carbon, oxygen, carbon. And if I put three hydrogens around here, they got to be singly bonded. And so that I stay in line with the octet rule, that carbon's going to have a single bond with the oxygen. This one's going to be single bonded to this one because I have three hydrogens on it. And then this oxygen will have two lone pairs. Now, in a little bit, I'll kind of show you some common bonding patterns that will demonstrate, why I'm showing that oxygen always with two lone pairs on it. Now, how does this compare to that second formula there? So this is kind of a part of the notation of these condensed formulas. If you see something that's got parentheses around it, what that means, like it means for this oxygen here, that oxygen is bonded to that carbon and that carbon only. Now, what does that mean for that middle one? Well, that middle one is still bonded to this first carbon, and then it's bonded to that one. So how do I draw this as a Lewis structure? Well, I'm going to put my three carbons in a row, and I'm going to show my oxygen here, bonded to that carbon in the middle. So I'll put my three hydrogens here, and it's single bonded to that carbon. And I'll do the same thing for the other side. Now, what does that mean for that carbon in the middle? How do I, do this? If I just have a single bond here, notice that that carbon is not happy. It's only got 6 valence electrons around it. So it'll be happy if it shares a double bond with that oxygen. And then that oxygen has two lone pairs. So the key thing that I want to highlight here is that when you see that parentheses in a condensed formula like that, it means that that atom in parentheses, or that group, it could be a group of atoms, is bonded directly to that atom that precedes it and no other atoms. So now, let's take a look at some common bonding patterns. And these are kind of like, this is the majority of the time. I'm not going to say that there are never any exceptions. There will be exceptions, but those are going to be kind of special cases that we'll highlight as we go along. But carbon generally forms 4 bonds. And that could be a combination of different types of bonds, like 4 single bonds, or a total, like a double bond and 2 single bonds, or maybe a single bond and a triple bond. Okay, the kind of key thing here is it's got a total of 8 bonding electrons. Now, nitrogen generally forms 3 bonds around it. And most commonly, that's 3 single bonds. And 1 lone pair. Now, you will see, well, this is kind of one of those special cases we'll talk about a little bit later. Nitrogen with a double bond to it, but still a total of like 6 bonding electrons around it. Oxygen, you'll typically find with 2 bonds around it. So something like 2 single bonds and 2 lone pairs, or a double bond with 2 lone pairs. But the trend that you'll want to remember is that there's usually 4 bonding electrons around oxygen and 2 lone pairs. Now, a common bonding pattern for halogens, and I'm going to throw hydrogen into here as well because they have the same bonding pattern, is that they will always have one and only one bond to it. For hydrogen, you'll never see it with anything else. Just one bond around it. Halogens, they'll have the one bond and then 3 lone pairs. We'll talk about some special cases down the road where you might see an extra bond to the halogen. It's kind of a weird case. We'll talk about it when we get to it, but 95% of the time, you're always going to see a halogen with just one single bond to it. So that's where we're going to kind of leave it with this brief lecture. When we come back to the next one, we're going to take our Lewis structures up a bit because you drew Lewis structures in general chemistry, and they were generally for small molecules. But in organic chemistry, we're going to start talking about molecules that have a lot of atoms in them. 10, 20, 30, 50, hundreds of atoms in there. And nobody wants to draw out all of those carbons, all of those hydrogens. So what do we do to represent these compounds that give us the same information, but allow us to be, I don't want to say lazy, but allow us to represent the same information, but just a lot easier. So we will get to that in the next lecture. So I will see you then.